Hello class, welcome once again. This is Benjamin Ahenkra, your lecturer for Biophysics. We will be tackling sedimentation techniques. So as part of the lectures, we'll be looking at the theory and forces involved in sedimentation, types of sedimentation, applications of sedimentation. Now, what is sedimentation? Theory and forces. Sedimentation is a physical treatment process used to settle out suspended solids in a fluid or a liquid medium under the influence of gravity. Looking at the diagram here, this is what? Water containing insoluble impurities. Insoluble, the impurities should be insoluble. So this water, you can say that it contains particles of sand of different weight and different sizes and shape. So when we shake up this water, when we mix up this water vigorously, the sand particles will float. Yes, the sand particles will be proportionally dispersed throughout the water. But when this medium settles, after settling, we realize that the heavyweight particles or impurities settle at the base of this container, whereas the lighter weight will float. So you can see over here that we have only the particles for the impurities are of the same size. So they all settled at the base of the container, whereas the water molecules or the water is displayed. The water is displayed at the brim. The water has a lighter weight. So the water is displayed at the top, whereas the sand particles, which are heavyweight, are displayed at the bottom. So we continue by saying that sedimentation is a method of separation of mixtures. Sample to be separated is mixed with a solvent, which is water, and stirred or shaken so that its components are randomly distributed in the solvent. Mixture is left for a while until the initially suspended particles come to rest against a stationary boundary due to action forces. And three forces come to play in sedimentation. We have the force of gravity, and we have the centrifugal force, and we have buoyancy. So, particles settle according to size. Like I said, heavier ones will settle first, followed by the next, and so on. So heavy particles will settle first. It's like you are mixing garri. When you are mixing garri, you realize that heavy particles will settle first before the lighter ones. You're mixing sand. Heavy sand particles will settle at the base of the container first, followed by the lighter weight ones, and it will form a band. So, let me explain this diagram. So we see that the base has coarse settleable matter. The base, the particles are very coarse, irregular shape, very big gravels. Then the next one is a fine sand. This is another layer comprising of fine sand. Then the next one is very light particles inside this mixture. Then the floating matter are leaves. You know, leaves are very light weighted, so they are floating on the surface of the water. So the only principle behind sedimentation is that the large and the heavy particles settle faster in a medium. The key requirement here is particle size under gravity. Components are insoluble. Dilute, when I say dilute, it's not that they can dissolve, they cannot dissolve, they are insoluble, but their surface can adsorb, not absorb, but adsorb water. So they can be wet, the surfaces of the particles can be wet with water, but they cannot dissolve in the water. The particles are large and rigid. Components to be separated are adsorbed in a solvent. Yes. Differences in shapes, masses, and densities are the main factors for separation. Let me take it again. Differences in shapes, shape of the particle, mass of the particle, and densities are the main factors for separation. We will look at that later. The process depends on gravity. The process is reversible, meaning that if you have a mixture of muddy water or clay and you mix it vigorously and you put it down to settle, afterwards, if you exert some small pressure to it, then it will form a mixture again. The particles will be redistributed all throughout the container. So you cannot see fine layers of sand, clay, whatever, no separation. Everything is going to be what? Mixed up. So we say that sedimentation or separation is reversible. The components are separated into layers called bands. So you can see this is one band, another band, another band, another band. So band 1, band 2, band 3. So this one has 3 bands and the leaves are settling on the top. Separation is not instantaneous. It takes some time. It takes some time before separation can be effected. And the process of separation is not affected by solubility of components, meaning that the components don't necessarily have to be soluble. They shouldn't even be soluble. Yes, garri cannot be soluble in water. Sand cannot be soluble in water. And this is what triggers sedimentation, or this is what makes sedimentation very essential and special. The process does not depend on the pigment of components. Yes, when we look at this process of chromatography, if you have maybe an ink or a paint and you want to separate the content and know the component of the ink or the component of the paint or the component of a dye, different colors of a dye, then you use chromatography. But for sedimentation, you don't need, it doesn't depend on the pigment of the solute. So we can see over here, implementation of sedimentation does not require specialized skill. Separation can be made quicker by centrifugation. So you can see over here, if you want to separate the particles, because if you let it settle for a long time, it will separate. But in case you need the result so fast, then you put it in a centrifuge. So these are before centrifugation. You see that the particles were uniformly dispersed inside the liquid or the water. Now, after centrifugation, the particles settle at the bottom, at the base, and the water is upwards. So you can also see that when you are separating the component of a blood, you can see the tube contain the whole blood. Then after spinning for about 15 minutes, you can see a clear liquid. This one is called the plasma. The plasma. Then the red blood cells are here. We call them the packed cells. So let's look at the forces involved in centrifugation, sedimentation. One, we have the force of gravity that acts downwards. So that is what is pushing this particle through this liquid medium. Then we have viscous drive, that's FD. That is the viscosity of the solvent, the viscosity of the liquid that this small spherical particle is flowing, is moving through. There should be what? Viscous drag or viscosity. So so far as the medium is thick, it will not allow particles to flow through it like that. For instance, if you are stirring TZ and you put, when you are stirring TZ and you put granite inside TZ and it's a thick TZ, do you think the granite will separate, or the granite will settle at the bottom of the pot? No, because the TZ is thick, so it has a very high viscous drag, which is higher than even the weight of the granite. So we also have force that is associated with buoyancy. When we say buoyancy, when you put a ball in a swimming pool, the ball will displace water which is equal to the volume of the ball. So that water will prevent the ball from sinking. So the ball will float because it will displace equal volume of water, which is according to its own volume. So the water's weight will balance the weight of the ball and the differences in the force exerted by gravity. So difference between the viscous drag and the gravitational force. So the buoyant force will be the difference between the buoyant force, rather the viscous drag will be the difference between the gravitational force and the buoyant force. That gives us a viscous drag. Like the viscous drag will, maybe the gravitational force is 100, the force due to buoyancy is 60. The viscous drag will provide a force. So the difference in the force is what? 100 minus 60 is 40. So the viscous drag for the particle to float, the viscous drag should be about maybe 50 or 60. So if it is about 50 or 60, then it will be stronger to push the particle or suspend the particle so that the particle will not sink. So that is the physics behind sedimentation, the forces behind it. So let's look at it. Force of gravity keeps the solution in the container and pulls the particles to the bottom of the solution. Force due to buoyancy. The action of a fluid on particles immersed in it. Buoyancy will act on the particles in the suspension. What it does is that it tries to push them to the surface of the solution, even when the particles sink. Force due to viscous drag. Particles moving through a liquid experience a force opposing their motion due to the viscosity of the fluid, like I said earlier on. So that is viscous drag has to do with viscosity of the fluid. This viscous drag acts in the line of, but in opposite sense to the direction of motion. So as the particle moves downwards, the viscous drag moves upwards. Then the buoyant force also, force due to buoyancy or equal volume of fluid displaced by the ball or by this particle. It will displace equal volume of fluid, which is equal to what? The weight of this particle, or the weight of this particle, and it should be balanced with what? Force of gravity. So this viscous drag and buoyant force, force due to buoyancy, if they are able to, if they are the two of them, when you add them and they are equal to the force due to gravity, then the particle will suspend. But if the force due to gravity is bigger or larger than these two forces that oppose the movement of this particle, then the particle will definitely sink. So let's do some calculations. Earth's gravitational force acting on any body at the Earth's surface. So force of gravity acts on all of us. That is what keeps us on the Earth. And you know the Earth is circular, spherical. It's like a ball. And we are all suspended on the surfaces. So force due to gravity is equal to mass times acceleration due to gravity. You know the formula for force is mass times acceleration. But when it comes to gravity, then we use the G instead of the A. Okay, so M stands for mass of the particle in kilograms. G is acceleration due to gravity, which is a constant. That is 9.81 meters per second squared. For very small particles, this is an assumption we want to make. The concept of density, not mass, is what we use. So for a bigger particle, maybe a football going through a swimming pool, we can use this formula. But if it's a small particle like a sand particle or an egg which we have put inside water, eggs, so that they will sink, or sand particle or any small thing, then we assume that for very small particles like sand particles, even egg is big, so very small particle like sand particle, the concept of density, not mass, is what we use. And we know that density is defined as mass over volume. Mass, when we make mass the subject, then volume will multiply the density, so that we get mass is equal to volume times density. So rho is for what? Density. Then mass and or whatever. Let's go. So force due to gravity. So assuming the particle is perfectly spherical, its volume can be calculated from its radius. Okay, so this volume over here is the volume of a sphere. This is a formula. I did not derive this. It's a constant formula. 4/3 pi r cubed. That's the formula for a sphere. Because we are assuming that the particle is spherical and very small. So, R stands for radius, which is measured in meters. Pi is the ratio of circle circumferences to the diameter, and pi is given as 3.142. Volume is meter cube. So combining equations 1, 2, and 3 gives the required result. So force due to gravity is what? 4 over 3 pi r cubed. Then density and acceleration due to gravity. How did we get this formula? Let's go back. So we have this initial formula, equation 1. We need the mass to calculate the mass, and we assume that for very small particles the concept of density, not mass, is what is used. So we don't need mass, we need density. So now we are going to calculate this mass using this density and volume. But density is equal to mass over volume. So if we want this mass, then we make this mass the subject, giving us density times volume. So when we go, then we need the volume, because the mass is equal to density times volume. So we need the volume. So this is the volume. So if you go back and put this volume in that formula, in this formula, we get the 4 over 3 pi r cubed density. Then wherever we see this m, we put 4 over 3 pi r cubed times density at over here, and that is what gives us this final answer. The starting point in calculating the force of buoyancy is Archimedes' principle. Archimedes said that any object wholly or partly, wholly means that totally immersed, or partly or partially immersed in a fluid is buoyed. Buoyed over here means that there is buoyancy. Buoyancy means that that particle displaces equal volume of the fluid which is carrying it. So the particle is in the fluid, but the particle has to displace equal volume of the fluid which is equal to the volume of the particle. And this volume of fluid equal to the volume of the particle is also equal to the weight of the same particle or object. And that is what we call force due to buoyancy. So force due to buoyancy for a spherical particle of radius r immersed in a solution of density ρ, the buoyancy force Fb is given by Fb is equal to 4 over 3 pi r cubed pq. And the buoyancy force, as initially indicated, is equal to the force due to gravity. So you can see that 4 over 3 pi r cubed rho gravity, acceleration due to gravity, is the same as what we derive for gravity. The only difference is that we have written Fg, that is gravity, but this is the same. When we come here, it is Fb, force due to buoyancy, and it's the same. 4 over 3 pi r cubed pq is the same as what we had for the gravity. The only change is this letter, B for buoyancy, and G over here for gravity. So, please, volume of fluid displayed is equal to 4 over 3 pi r cubed. And like I said, the volume of fluid displayed is equal to the volume of the particle which has been suspended, which is floating or which is sinking in the medium. Okay, so we have density is equal to mass over volume. Mass equal to density times volume, because we multiply volume by density to get mass. So mass equal to, so mass of fluid displaced. So we want to know the mass of fluid displayed. So mass of fluid displayed is equal to density times volume. And whenever we see volume, because it's a spherical particle, we bring 4 over 3 pi r cubed. Okay. So for buoyancy, force due to buoyancy, which is here, is mass times acceleration. We are trying to derive the formula. Okay. So let's now look at force due to drag or viscous drag. That is force due to viscosity of the fluid, because you can't put, for instance, if you drop a particle into an alcohol, then you drop the same particle into porridge, you don't assume that they all float, because for alcohol it's less dense, so the moment you put it inside to get to the bottom. But for thick porridge or thick dessert, when you put it inside, the viscous drag or the viscosity of the fluid will prevent the particle from sinking. So let's look at the formula for viscous drag. This is, I will not show you how it is derived, but just know it. But I will not be asking you to write this formula in exams. So force due to viscous drag is equal to 6 pi r, this sign, and also velocity. So this sign is a constant. This sign looking like n is a constant denoting viscosity. It's a constant denoting viscosity. So r is the radius of the moving sphere. This one is viscosity of the solution measured in Pascal. Then v is the velocity of the moving sphere. So this sign is the viscosity of the solution, which is a measure of the resistance to flow in a liquid. So the viscosity is what will resist the particle from flowing, the particle from settling at the bottom or sinking. So Stokes' law applies to a spherical body and non-turbulent flow. So I don't know what Stokes' law is doing over here, but Stokes also said that his law applies to spherical body and non-turbulent flow. So this medium, for a particle to sink, there shouldn't be any turbulence or there shouldn't be any disturbance in the fluid. The fluid should not be moving up and down. No, if it happens like that, the particle, it will be difficult to see separation of the various particles, because when you mix sand with water, when you shake it, you have to put it down to settle. But if there is turbulence, that means that there is still shaking. The particles cannot settle. So, sedimentation of a small sphere in water. So combining the results from the theory of sedimentation applied, it follows that if a particle is suspended in a container of water, it will immediately experience a force downwards due to gravity and a force upwards due to buoyancy, like I said. Assuming the density of the particle is greater than that of the surrounding solution, gravity will win, and the particle will start to fall towards the bottom of the beaker or the container. As soon as the particle starts to move, the viscous drag will come into operation, opposing the motion. As the particle accelerates or moves faster, so the viscous drag also increases, that the viscosity also increases, until the viscosity of the fluid or the medium increases, until this drag force just balances the difference of the gravitational and buoyancy forces. So when the viscous drag balances the difference, meaning that as the object is moving through the liquid or the water, what happens is that the buoyancy will try to prevent it from flowing, from getting to the base or from sinking. But if it's not able to succeed, then the viscosity of the medium or the fluid will also come to prevent the same object from settling at the bottom of the container. If this viscous drag also fails, then the object settle at the container, the base. If the viscous drag does not fail, then the object will settle, will form a band, or it will settle, it will be suspended at wherever location it will get to. So we can see that when we separate sand and other things, we can see the clay going down, the clay being up, the sand, the coarse particle of the sand, or the heavy ones, going down. Then the fine particles settling on top of the heavy ones. It's all because of these three forces. So, combining the results from the theory of sedimentation outlined above, at this stage, the particle will continue to fall through the solution towards the bottom of the container, moving with a constant terminal velocity. So the particle will continue to move to the bottom of the container, and by so doing, it moves with a constant terminal. Terminal means the final velocity. The value of the terminal, that's the Vt, velocity, can be determined by equating the three forces. So this is, we know that this is the viscous drag. Then we have factored the radius of the volume of a sphere out. So this is density due to what we call gravity. Density for the gravity equation, and this is density for the what we call it, the buoyancy. So when we factor everything out, this is what we get. I don't need you to chew these formulas. So at this stage, the particle will continue to fall through the solution towards the bottom of the container, moving with a constant terminal velocity. The value of Vt can be determined by equating the three forces. Okay. The time for all particles in the solution to migrate to the bottom of the fluid under gravity is T is equal to this. There are four types of sedimentation processes. There is the dilute, non-flocculent, free settling. Every particle settles independently, and this example of this is a mixture of sand and water, or a mixture sand that has been mixed in water. Then the second one is dilute flocculent. Particles can flocculate as they settle. When we say flocculate, meaning that they aggregate together, they form something like a wool, aggregate together, they clamp together, like a thick clay, the way clay is, clay ball. Okay, so this one, an example is a mixture. An example of the second one, this one, is a mixture of clay, sand, and water. Because you can see that there is dilute over here, meaning that it's not able to dissolve the particles, but the solvent is able, or the solution is able to absorb or wet the specimen surface or the particle surface, but it's not able to dissolve it. So we have the dilute, we have the flocculent, that's forming like a clay ball. Particles can flocculate as they settle. So there's a mixture of sand and clay. Then the fourth one is concentrated suspensions. Concentrated suspensions, zone settling, or sludge. So this one can be compared to muddy water. Muddy water. You know, it's concentrated and it's a suspension to zonal settling, but it is very thick like TZ. So we call it, we can say that it's like muddy water, or muddy water, or what the mud that they use to prepare these clay pots and earthenware pots and those ones. That's how they make it, very thick. Then the fourth one is concentrated suspensions, compression, sludge thickening. So the fourth one is, excuse me to use this example. Toilets, KVIP, latrine. You know how the toilet is very thick, concentrated suspension, compression, sludge thickening. That is how toilet is. Toilet in a KVIP or in a pit or in a latrine. That is how it is. That's the fourth one. So what's the relevance of these sedimentation types or techniques? One, when you go to water treatment settings or water treatment industry, they use this sedimentation to separate the component of water or to treat water so that the water will be passed through sand bed. It will filter the debris or the different particles from it. The sand, you will filter the sand, you will filter everything. So you have to mix the water and let the water settle so that you pour the clear water out so that the debris you throw away. Then, so example is wastewater treatment. If there is any wastewater, you need to recycle the water to then you use this sedimentation technique to treat the wastewater because nothing should be waste. Then separation of muddy water, yes, it's like the type 3. Examination of soil profile. Okay, so the agriculturists and the rest, they do soil profiling to know the type that is good for them to plant which crop or which specific crop for the season. So they need to profile the soil to see. So they use sedimentation techniques. Then if you want to separate blood components, like what is in this slide, let's visit this slide. Yes, if you want to separate these blood components, you see we have the plasma, we have the packed cells. So we use centrifugation to make it faster. So if you want to separate blood components, it's also a means of sedimentation. Then the last one is separation of specimen in fluids, like bacteria and others. You want to separate them, use sedimentation. So for instance, in the urine, if you bring urine to the lab, after we've done the urine chemistry, we want to also see whether there are past cells, epithelial cells, and other things, whether there is candida, whether there is this. So we separate the components before we culture for the bacteria so that we can provide the needed sensitive antibiotics that the organism is sensitive to, that we provide that panel for the doctors to make their prescription. So you can see that the laboratory is very important, because if a laboratory man says, or if the laboratory diagnoses a condition, the doctor has no say than to prescribe those drugs, or to say that the laboratory man, what he's saying is the truth. So doctors really are afraid of the laboratorians. Doctors are really afraid of us because we know what we are about. So the last two applications usually require the use of a centrifuge. So separation of blood components, separation of specimen in fluids require a centrifuge. Class, thank you very much. If you have any question through this lecture, you can pause this recording or this video and note down your questions so that when we come to class, I will answer them one by one. Thank you very much.